This is the offset, and this is the page number. So this is a new address format, considering the pages. Okay? If we do not use the page, we can just specify the location of the instruction program counter address directly. However, in this case, in the case of the paging, so we need to specify which page it is. Then this second part is the offset, how far from the here to here. Then think about the 16-bit at the computing, the system. 16-bit means we can represent up to what? 2 to the power of 16. Okay? So address, because the maximum is 11111111. This, the 16-bit is used for what? Address. So your address, even though you have the, for example, so I think that you probably lived at the time 2000. So what happened from the year 1999 then to the 2000? What happened in the IT department at that time? Do you know? It's called the Y2K. The most of the system use YY. Still, some of the documents still use the DD, MMYY. So to represent the year, so we use the 2 digits because it was enough the 96, 99. But the problem is the 2000. So that is the win-win. Alright, the 00, whether this is a 1900 or 2000. So to change it, replace all of this format into the YYYY. We spend a lot of time because somebody there might be the exploding or accident, but which didn't happen. But this is because this is limited by the YY. Okay. So this is a data structure for the year. But after changing, we can represent much flexible. Up to the 9999, I'm not sure the human being can survive at this time. So this is a flag. Same thing for the 16-bit processing, which means we can represent 16 digits of the binary number at the same time. That is the limitation of our addressing. Okay? Even though you have the bigger size of the land, if your address format is limited, that's the maximum amount of you can own. So this is the same thing. So if you are using the 16-bit processor, then it can understand up to the 16-bit. Then this time we need to divide this address 16-digit number by 2. One is used for page number, another one is for offset. Then at this time, offset. What is the maximum size of the offset? It depends on size of the page. Okay? So for example, if we are using the 8, the byte, the page size, how many bits do you need to represent the 8? 3 is 3, right? So 3 is enough. 111 is the 8, the 7th. So 0 through 7. So we need the 3 bit. Then the other 13 bit is used for what? Number of pages. So you can have a total 2 to the power of 13. The number of pages in your system maximum. Because of that, the limitation of address. So long time ago, when you are using the 32-bit the process, your file size is limited by what? 4 GB, or some of them is 2 GB. Nowadays, the 64-bit, the virtually unlimited, but it's actually limited, but we may not have such a number limitation, maximum size of the file. But when we use the 32-bit processor, it's actually problem is the addressing. Because of addressing, so we have the less than 4 GB, the file size. That's the limitation. Some of the operating system is 2 GB. But anyway, so we are going to divide the addressing the format, the page number plus the offset. Offset will be determined by the size of the pages. So what about the 512 byte? The page size. How many bits do you need to represent the offset? 512 byte. 9. So 9 bit is used for offset. Then how many bit used for the page number? In the 16-bit process. 16 minus 9, 7. So 2 to the power of 7 is the maximum number of pages. Even though you have the bigger size of the memory, physical memory, you cannot use all of them. That's the reason always is that when you make your own computer, so your memory slot and memory size is limited, maximum limitation. You need to check the processor type and the motherboard and so on. So that is the addressing, new addressing format used for the pages. So page number plus page offset. Then finally we can implement, the CPU vendor can implement the hardware for the paging to support. Basic idea is the same as the previous one. Segment based or the contiguous location. First, take a look at the address. P is the page number and D is the offset. P plus D. This is the address. And check. We don't have to worry about the offset. Offset will not be changing. But page number, this is the logical page number. So we need to know physical page frame number. From where? Page table. Take a look at the page tables and the page frame number is F. Then replace the P by the F plus D. So F, you can find the F, then finally add the offset, so you can access the physical location of your instruction. So this idea is all the same always, okay? But depending on which the scheme you use, is slightly different. Okay. So this is one of the examples of using the page for the program and the physical memory. Then this is an example. So in this example, we'd like to find the physical address, okay, from the given the system. Let's say that this system has used the paging. It's a paging approach. So which means the fixed size of the unit. For both, this is our program logical memory. Right hand side is what? Physical memory on your computer. Okay? Then this time we are going to use the 4 byte as the size of the page. So we are going to divide the both logical memory and the physical memory by the page size of 4. So divide by 4, 4, 4, 4. How many? The pages in your program. 4 of them. So we can number from the beginning 0, 1, 2, 3. My son is 7 years old, so I tried to teach the program language, Python, before, but he gave up right now. One of the question, mostly asked the question is why computer start with always 0? Why? So instead of 1, 2, 3, you never thought about it. So we always starting the number, the 0. But in natural number, the human being, mostly familiar with the natural number. Natural number system is starting 1. Okay. Actually, we didn't have the 0 before, long time ago. But starting with the 1. But the computer always started with the 0, 1. It's a binary system. So binary system can start 0, 1, 0, 1, 0, 1, starting from the 0 to represent the beginning, 2 to the power of 0, 2 to the power of 0. Okay, so 0, 1, 0, 1, 0, 1. So because of that, because one of the students long time before, I didn't mention the 0, 1, 2, 3 here. And complain. I consider this is 1, 2, 3, 4, like that. And this is 1, 2, 3, 4. Okay, even though I do not mention the number starting with a 0, but it's not most, all of that, such a numbering. In the computer science, it's a 0, starting with a 0, 0, 1, 2, 3. So it's a page number 0, page number 1, 2, 3. Then this one is a page frame number 0, 1, 2, 3, 4, 5, 6, 7. Total 8 page frames. So at this time, so as you can see, it's a 32 bytes of the physical memory. For example, logical address, to represent the logical address, you should have page number plus the offset. So for example, what about F? F is the page number what?
1.
Page number?
1.
F is the page number 1 and offset?
1.
0, 1. Always start with the 0. So 1 and 1. So this is the page number, this is the offset D. Then check the 2, find the physical location. You cannot read that directly from the memory, the program. CPU, no, would like to know the physical address. Then check first, check the page table. With the P, the 1 is mapped to the 6. So this one is the 6. Then the offset is the same thing. So 1, so 6 is the 6 times what? Page size. 6 times 4, right? And plus offset 1, this is going to be 25. So 25 is here. Then read this instruction, the transfer to the register, then process this data by the CPU. Okay? This may be the good question for the final exam, right? No? It's very simple. If you are not sure, this is just 3. Actually, I didn't. If I'm asking what is the physical address of this one and this one, sometimes you can count. If I give this information, you can count. You can just check the 25. So in your exam, I will not give this side. Okay? And little bit more complicated. But in this example, actually you can check where is the F. This. Okay? But sometimes I will not give the physical memory. Okay? Then you can, without this information, you can calculate always the physical address or vice versa. If I give the physical address, you can calculate the page number plus offset. Okay? So you should be able to both of the ways to convert the logical address and the physical address. Any question for this? Looks like a very simple elementary math, but surprisingly, in the exam, less than half. Really. So please practice just one time, at least one time. Okay, and this is somewhat the example to calculate what is the internal fragmentation and so on, so you can quickly. What about the internal fragmentation? Here. This still has the internal fragmentation, sometimes a little bit more serious than the segment-based or contiguous approach. But sometimes we can intentionally, some of the similar approach intentionally put the internal fragmentation also. The next issue is the free frame. The free frame means we need to know in the contiguous allocation, like the partition-based contiguous allocation, we use the first fit, the best fit, or the worst fit. But here, what we need is the free frame, which is not occupied, which means we need to, just like the free block in the photo file system, we need to manage such a list of the free frame. Okay, free frame list. Okay, like the page 0, 1, 2, 3 this is a before allocation, so this is a free frame list. You can manage the free frame list. Or just like what you implement, we can have the sequence of bit 2 byte or 3 byte, and 0, 0, 0, 0. 0 is used and the 1 is free, and so on. So either of them is fine. So anyway, so we need to manage the free frame and allocate for the process. Okay, so as I mentioned, this page table should be in the memory, which means the CPU should know where is it. So that is the PTBR, the page table base register, and page table length register. Okay, so far so good. Problem? One of the problem is this one is small. Even the free frame list is small, so it's 32K for example, and with the page size 8. What about the memory size? What is your memory size? Yeah, RAM. 8 GB. Then how many pages do you have? If you have the 512 byte, divide by the 512 byte. It's huge, right? So number of page frame is huge, and also your page table is very long. It takes a time to find, even, right? And whenever, how often the system would like to access such a page table? It's a lot or very rare? It's really a lot. Whenever CPU access any instruction, must check the page table. It's a lot of I/O. Even though that is in the memory, if it's too much, it will be overhead. So always I mentioned that if by considering long time history of the computer and computer system, computer science, whenever we encounter problem of the speed, how did we address such a speed gap, speed problem? How? Always cache. We can use the cache area. Cache means instead of accessing the main primary, the storage or the data, we can keep the sum of the frequently accessed data in the fast media. Similar idea, so we are going to put the cache of the page table. Usually the table will be in the fast media. This one usually in the main memory. But this one in the add to cache or the cache area for the CPU. So what is this? This is the same as the page table, but this one has the sum of frequently accessed pages. This is true. I already mentioned in the disk management. We don't access all the data in your file system. Even you don't know how many file, what kind of file you have, even though you create the folder. Okay? Sometimes you will surprised. Did I take this folder? So a lot. So not a lot, the few of them you are accessing. So same thing in even the memory. Not all the page frames are accessed. If you check your physical memory, so surprisingly, your system is right now the 70–80% of memory RAM you are using. Not all of them you are currently use such a thing. So from that idea, why don't we keep the frequently accessed page and the page frame number information in the TLB. TLB is the translation loop-aside buffer. Translation loop-aside buffer. It's a cache for the page table. Okay, mostly this is in the fast media, like the add to cache and so on. Okay, so how can we use? This is a big or small. It doesn't have to be big. If big, that's the same problem as the original page table. We just keep the frequently accessed entry. So that is the TLB. So it's usually the 64 to the last number, much less than the physical, the page number. Yes. The translation loop-aside buffer, we translate the logical address to the physical address. Okay. So then there is a kind of lookup table. So lookup table is a cache area. So how can we use? The same idea, the page number and the frame number. But first, the CPU would like to read the instruction from the memory. It has the P plus D. P plus D means logical page number plus the offset. So then, instead of accessing the page table directly, because it takes a longer time, we first take a look at the TLB, the look up the table. Then check whether this page number is in the TLB. If yes, that is called a hit. Usually we are using the terminology as a hit. If you can find something data from the cache, okay? Otherwise, it's a miss. So hit, in case of a hit, so you find the frame number, then convert the logical, the page number by the physical page frame number. Still, D is the same, the offset, then finally access. Otherwise means if you cannot find the entry from the here, you cannot find the page number, which means it's not frequently accessed, and you can take a look at this one, page table, then the replace. At this time, you can enhance the performance of this one a lot. Like for example, if this one is missed, then this entry will be in the TLB. Or there are different ways. Like if you think about the linked list, I think that there is a specific name of the linked list. If you access the one data, it will be promote. What is the name of that linked list? Something specific name. Optimized version of the linked list. You can move up, then finally most frequently accessed the entry will be nearby the header. Okay? So similarly, you can implement such a thing in the TLB. Okay? So this is the what? By the way, both of them is a hardware implementation. So you need to implement this one. Not unit to. So it's implemented by the CPU vendor who provide such a thing. Okay, I'm going to skip the effective access time. You can easily calculate what is really the benefit of using the TLB by considering the hit ratio. Hit ratio means the number of entry accessed from the TLB over total number of accessing. So how percentile or the ratio that can be accessed by the TLB. That is a hit ratio. Then you can calculate the benefit of this one. Okay, then so far we can use the base and the limit to protect the process, each process, because the memory is nothing but just address. There's no clear boundary. There's no fence. So if you know the address, you are able to access the data in that location, then it will cause the problem. So to protect in the contiguous location, because it's a contiguous, we can just limit starting and end. If your address instruction is in between, it's okay. Otherwise, you get the thread or interrupt. What about the pages? Page is spread out, as you can see here. One page is here, another page here, like this. Which means you cannot check each and every time. Instead, to protect the process, we are going to consider the data structure that is the valid invalid bit. Valid invalid bit means, so in the page table, for each process we are going to manage the page table. It's a per process. Okay? But if this page table map the different one, because not always, so for example 0, 1, 2, 3 and 3, 8, 7, 1 and so on. Sometimes later we will see the later page out, which means if you need the free frame, we can remove this one. Then or sometimes make the free frame. So this one is still there because it takes some time to update, to remove the entry. Instead, we can put the valid, invalid, valid, invalid. Invalid means it's no longer existing. Okay? And this one, no longer existing. So instead of removing the entry from the page table, we can mark just one bit, 0 or 1. Valid, invalid bit. So usually 1 is valid, 0 is invalid. So for example here, so V means it's a valid. Okay? So first check whether this page frame is valid or not. Because when we move out, for example, later for the several reasons, so we can take out the page 0. That doesn't mean we remove the page 0. Think about your file system. When you delete the file, do you really delete the file from the file system? Instead, just from directory, you can take out the FCB only. Same idea, when we page out from this physical memory, we do not actually delete the information in this page frame. Instead, just update invalid. Then we can reduce a lot of file in the memory. So this is a valid, invalid bit. So because one program is separated by number of pages, we cannot actually clearly define this is a starting, it's the end. Instead, page by page, we can set up that this is valid and invalid. So that is valid, invalid. Also, another benefit of using the page is what if we have the number of the process. We have another process and the number of pages. Think about the Microsoft Word. When you can edit the two documents at the same time, right? It's multitasking. You can click A.doc and the B.doc. So how big is the Microsoft Word? So several hundred megabytes. And also memory is a lot. At least 80 or almost 100 megabytes. The memory you can use. Then whenever you click the new document, do we need the same code of the Microsoft Word in the memory? Actually, we don't have to. It's the same program. Instead, we can use the same code for the Microsoft Word itself. Then change the name of file and the document specific information. So that's the idea of the shared page. So when we run the multiple processes, multiple logical memory, then if possible, we can share the pages. So instead of creating the new page frame, we can just this one, two, if they are the same code. So that is called the shared page, which is not possible in contiguous allocation. But in the page, it is much easier to use the shared page. So this is an example of the shared page. For example, ED1, ED2, ED3 is the Microsoft Word. And ED1, ED2, ED3 is Microsoft. Only difference is the data itself, document itself. So we can use the same. For example, the page table for 0, 1, 2, 3. The 3, 4, 6. 3, 4, 6, as you can see, it's the same code. So we can save the storage of the memory using the shared pages. Okay? That's very short. Then, this one, also the problem. So as I asked you, if you have the 16 gig, the size, the RAM, the memory, the size of the page table will be huge, right? It takes a long time and it will be hard to manage this just a sequence. So, to manage the page table, the sequence, the list of just the pages, not very effective in case you have the bigger size of the memory. So there are different approaches to organize such a page table. Okay, so one is a hierarchical paging, and another one is a hashed, and third one is inverted. First, hierarchical. This is our page table. What is how many of you are taking the database or took the database before? I think that you must. Both of them operating system database. The core course for MSCS. In the database, what is the main purpose of the database? Using database. Why do you use database? Store the data. You can store the data in the file system. Organize data. Why do you need to organize? Type. And also there are several, actually many reasons to use the database. Most important part is search the data. Okay, that is the main. The more data you have, the longer time to search the data. Our main goal, first goal of using the database is when we have. So Dr. E.F. Gold proposed the relational database model long time ago, 1969 and 70. At the time, his paper titled as a very large, too many the very large. We need to know the data structure that is a relational database. Actually, it was not the really big data, very large database. At that time, it was a very large database. So how can the database the speed up to search the data? One of the way is you can use the better performance, the hardware. Also second, as we discussed a lot, memory. We can use, actually the database uses a lot of memory. So mostly if you are installing the Oracle, MySQL, Informix, any the database management system, you are asked to use the half of the physical memory for database, or the minimum requirement. And the third approach to speed up to search the data is indexing. So indexing is the different data structure to organize the data, just like the textbook. If you take a look at the textbook, when you search the page, how can you search the page? One student look up from the page number 1, number 2, number 3. If you are a little bit smarter than that student, you can check the TOC, table of contents, right? So first chapter, second chapter, third chapter. But I believe that you will check the index and at the end of the textbook, then it's organized by the keyword and sorted. Then there is a page number, then go to the specific page. Same thing. So if we have the bigger size of the page table, why don't we keep the index of this one, outer page table? What if this one is also too big? We can make another level of outer page table. So eventually this will be hierarchical tree structure. So that is but it's not like the search tree in the database. So usually 1 or 2 level of the tree hierarchical structure. So at that time, our page, our address format should be changed. For example, in case of the 2 level, this is a page table for this one. This is a page table for this one. So the address format is a page 1 and level 1 and level 2. So depending on how many the page table and how many page table, you can allocate the different number of bit. So addressing format for the hierarchical page table management, 2 level paging, you have the 2 level to the number of the page table. Then finally using this one, you can find locate the address of the disk and address of this. Finally, you can get the physical address of the logical address. This is an example of the 32-bit the addressing format. Okay, so divide by the how many bits? This is 8. Up to 10 is used for the disk, and up to 10 used for bit, 12 bit used for the offset. So 2 to the power of 12, which means the 4K, the page size. So 4K by the page size of the